Okay, so picture this. You've been working for hours on a project, you finally got it just right, and you move your mouse up and you click save. It's an action you've done thousands of times, probably without a second thought. But have you ever stopped and really wondered what happens in that split second? I mean, what's really going on inside the machine? What incredible high-speed dance of hardware and software is happening to make sure that your work doesn't just, vanish into thin air? Well, today, we're going to pull back that curtain. We are going to dive deep into Chapter 10 of our operating systems text, Mass Storage Structure. We're going to explore that hidden physical world that lives right behind your screen. All right, so here's our game plan. First up, we're going to look at the hardware itself, what's actually inside your hard drive. Then we'll see how the operating system has to step in and tame this wild piece of hardware. After that, we'll play a little game I like to call the elevator scheduling game to understand how we get performance out of it. Then we'll see how your disk can be a hero and act as emergency memory. And finally, we'll cover something absolutely critical, a technique called RAID, which is all about making sure you don't lose your data. So let's start at the absolute ground floor, the physical hardware. When you save a file onto a classic traditional hard drive, you're not just dealing with abstract bits and bytes. You are commanding a tiny, incredibly precise piece of mechanical engineering. I want you to imagine a stack of tiny, super fast record players. Each one of these disks, which we call a platter, is spinning at an insane speed. We're talking thousands of revolutions per minute. Floating just nanometers above the surface of each platter is a tiny read-write head, and that's attached to a moving arm. Now, your data is stored on these platters in concentric circles, kind of like the grooves on a record. We call those tracks. Each track is then chopped up into smaller pieces called sectors. And if you imagine looking down through the whole stack of platters, all the tracks that are in the same position on each platter form a vertical cylinder. So, to read your file, that arm has to physically race to the correct cylinder, and then it has to wait for the exact right sector to spin around and pass underneath the head. It's an amazing physical dance. But of course, these days, we're all hearing about solid-state disks, or SSDs, right? Now, unlike that mechanical dance of the hard disk drive, or HDD, an SSD is pure electronics. There are no moving parts at all. You can think of it like a really, really big and fast USB flash drive. And because there's no physical movement, access is almost instantaneous. So what's the trade-off? Well, as you can see, the classic HDDs with all those moving parts are slower, but they're way cheaper per gigabyte. You get a lot more storage for your money. SSDs, on the other hand, are blazing fast, but they're more expensive. And the operating system has to be smart enough to manage both of these very different technologies. Okay, so now we've got this piece of hardware, this collection of spinning platters or fancy memory chips. But here's the thing. A brand new disk, fresh from the factory, is totally useless. It's just a blank slate, a chaotic, unstructured mess. Before you can save a single file, the operating system has to step in and create order from that chaos. And this happens in 3 really important steps. It all starts with something called low-level formatting. This is usually done at the factory. It's what physically creates those sectors on the disk, laying down the basic boundaries that the hardware controller needs to function. Think of it like a crew coming in and painting all the lines on a giant empty parking lot. Next up, the OS does what we call partitioning. This is when you might create your C drive and your D drive. You're taking that one single physical disk and chopping it up into one or more logical, manageable chunks or volumes. And finally, there's the part you might have actually done yourself, high-level formatting. This is where the operating system builds the actual file system. It's like building the card catalog and shelving system for a library. It creates all the structures needed to keep track of where files and folders are and what space is free. Without these 3 steps, your disk is just an expensive paperweight. Okay, now this is where things get really interesting. We've got our formatted disk, and the requests start pouring in from all your programs. Read this file, write this data, open that application. The single biggest performance problem, the ultimate bottleneck for a traditional hard drive, is that physical arm movement, moving that little arm across the platters. In computer time, that's an eternity. It is incredibly slow. So the operating system has to be super smart about the order in which it handles these requests. And this is what I call the elevator scheduling game. So the most obvious way to do this is first come, first served, or FCFS. It's simple, it seems fair, just like a line at the grocery store. But just look at our example here. Let's say the read-write head starts at cylinder 53. The first request is for cylinder 98. Okay, it moves there. The next one is for 183. Then, whoa, it gets a request to swing all the way back to 37, then out to 122, then way back to 14. The arm is just thrashing back and forth, zigzagging all over the disk. The total distance it traveled? A massive 640 cylinders. It works, sure, but it is painfully inefficient. So you have to ask, can we be smarter about this? Oh, absolutely. Let's try an algorithm called shortest seek time first, or SSTF. This is what we'd call a greedy approach. From wherever the head is right now, it always picks the request that's physically closest. So using the same request queue, from our starting point at 53, the closest request is 65, then 67. Then it jumps over to 37, then 14. And only after cleaning up all the nearby requests does it handle the ones that are further away. And the total head movement? It drops down to just 236 cylinders. That's a huge improvement. But there's a problem here, a dark side to this greedy approach. What if new requests keep showing up right in the middle of the disk? Well, the requests that are way out at the edges might get ignored for a really long time. We call this problem starvation. And that brings us to my favorite, the most elegant solution, the scan algorithm. But pretty much everyone just calls it the elevator algorithm. And for good reason. The analogy is perfect. The disk arm behaves just like an elevator and a tall building. It sweeps in one direction, from one end of the disk to the other, servicing every single request in its path. When it hits the end, it just reverses direction and sweeps back. So in our example, the arm starts at 53 and moves towards cylinder 0, picking up requests at 37 and 14 along the way. Once it hits the end, it turns around and sweeps all the way across the disk, handling everything else. The total movement? A tiny 208 cylinders. It's even more efficient than SSTF, and because it always services the entire disk, starvation is no longer a problem. So let's just step back and look at what we've done here. The main takeaway is that the algorithm the operating system chooses makes a massive difference in performance. This summary shows it perfectly. Just by being smart about the order of operations, by switching from that naive first-come, first-served approach to the intelligent scan algorithm, we cut the physical work the disk had to do by more than 2/3. This is the kind of magic that's happening behind the scenes that makes your computer feel fast, or sometimes frustratingly slow. All right, we've tackled the speed problem, but there's another big issue the OS has to solve, the memory problem. Your computer's main memory, the RAM, is super fast, but it's also expensive and you only have a limited amount of it. So what happens when you open just one too many Chrome tabs and you run out of RAM? Well, the operating system has this really clever trick up its sleeve called swap space. It basically carves out a section of your much slower hard disk and says, okay, this is now my emergency overflow area for RAM. When your main memory starts to get full, the OS looks around for chunks of memory or pages that haven't been used in a while, and it swaps them out onto the disk. This frees up that precious fast RAM for the programs you're actively using. Of course, when that swapped out data is needed again, it has to be swapped back in. This is exactly why your computer might suddenly slow down to a crawl when you have too many things open. It's busy swapping back and forth with a slow disk. It's definitely a performance hit, but hey, it's way better than just crashing the system. Okay, we've handled speed, we've handled memory. Now for the one that keeps us all up at night, reliability. What happens if your hard drive, this complex, spinning mechanical device, just fails? Is all your data, your photos, your work, your memories just gone forever? Well, not if your operating system is using RAID. RAID stands for a redundant array of independent disks. Now, the easiest one to understand is RAID 1, which is also called mirroring. And the name says it all. For every single piece of data your computer writes, the system writes an identical, perfect copy to a completely separate second disk, all in real time. It's literally making a perfect photocopy of everything you do. If your main disk suddenly dies, no problem. The system just seamlessly switches over to the mirror copy, and you don't lose a single byte of data. The downside? It's pretty obvious, right? You have to buy 2 hard drives to get the storage space of one. It's incredibly safe, but it can be expensive. Now, completely on the other end of the spectrum, you've got RAID 0, or striping. This one is all about one thing, speed. Instead of duplicating data, RAID 0 takes your data, splits it into little chunks, and writes those chunks across multiple disks all at the same time. You can think of it like having 2 people unload a moving truck instead of 1. It goes twice as fast. But, and this is a huge but, there is 0 redundancy. If any single one of the disks in a RAID 0 setup fails, you lose everything. Because all you have are incomplete pieces of your data. The whole thing is gone forever. So it's very high risk, but very high performance. So you might be wondering, is there a middle ground, a sweet spot between safety and speed?
You bet there is, and it's called RAID 5. And this is where things get really clever. RAID 5 stripes data across multiple disks for a speed boost, just like RAID 0. But here's the magic trick. For each stripe of data it writes, it also calculates and stores a special block called a parity block. You can think of this parity block like a little mathematical clue. If any one of the disks in the array fails, the system can look at the data on the surviving disks, look at that parity clue, and use them to perfectly reconstruct all of the data that was on the failed drive. It's a brilliant compromise that gives you great data protection without doubling your storage costs like mirroring does.
And this table really puts it all together for us, right? It's all about trade-offs. You've got RAID 0, which is all about maximum performance, but it has 0 fault tolerance. One failure and you're done. You've got RAID 1, which is all about maximum fault tolerance, but it comes at a high cost. And then you have RAID 5, which offers that beautiful, balanced solution, good performance and protection against any single disk failure. This makes it a super popular choice for things like servers and the giant data centers that power the cloud services we all use every day. The OS has to manage all of this based on what's most important: speed, cost, or safety. So when you zoom out and look at the whole picture, the smart scheduling, the swap space management, the RAID configurations, you really start to see the OS for what it is. It's the silent hero in all of this. It's this invisible intelligence that takes these raw physical pieces of hardware, which, let's be honest, are fundamentally slow, kind of dumb and fragile, and it transforms them into the fast, efficient, and reliable storage that we all trust with our entire digital lives. And that leaves us with a really fascinating question to think about for the future. As we continue to move away from these mechanical spinning disks and more towards pure electronics like SSDs in the cloud, which of these challenges we talked about today, like the elevator algorithm, will become totally obsolete? And maybe more importantly, what brand new, more complex problems will the operating systems of tomorrow have to solve?